My second question is, what is the importance here of the queue implementation? Okay, the queue implementation, if you remember, we have seen two different strategies. One was the best first search and the other one was the depth first search. So let's switch to the code here and consider the two possible implementations. Okay, so one possible implementation here is to use the best first search and the other one depth first search. And I will use here my weak relaxation, which is the one based on the capacity. So where was it here? Okay, I use the capacity relaxation. And the problem is that if I'm using the best first search strategy here, in that case, so okay, here I will use the best first search strategy. I will not be able to obtain quickly a feasible solution. I run this code and it's never returning. Okay, I'm waiting here and I don't get a solution. The reason that I don't get a solution is because the search tree is expanding in a breadth first search way. So we have a very large search tree and we are not able to even find a feasible leaf node here because the relaxation is weak. So it's always expanding according to the best upper bound, but the search is very uninformed because the relaxation is not very good, it's not very tight. And so the search tree is going out of control in terms of the number of open nodes. So it's not good. If the relaxation is bad, probably it's not a good idea to use best first search. If the relaxation is strong, best first search gives you quite good solutions. So let's switch to the depth first search, which might be a better choice in that case when the relaxation is weak. Okay, I will stop the code, execute it here. Okay, and you will find that I'm able to find a good solution quite quickly, even with depth first search, but I'm not able to prove that it's optimal. Okay, but this one is the optimal one, and it's able to find it. Okay, but it's not able to prove that it's the optimal one. It's still trying to prove it, but I have no idea how long I need to wait to prove that it's the optimal one. Okay, and my third question, my third possible choice was the importance of the heuristic here. Okay, what is the importance of the heuristic on the performances? And to implement the heuristic, I've got two possible ways to do it. A first heuristic that will impact a lot here is the way I add the children here in the queue. So if I select the item on the left or on the right, it will have an impact if I'm using depth first search. It will not have an impact if I'm using best first search, but for the depth first search, it will have an impact. If I switch the two, I will have a very poor first solution because I will select on the leftmost branch, I will not select the items, and the first solution that I will get is not to select anything. Okay, I do not select at all any items, which is a very poor objective function, of course. So this might already have an impact on the performance, okay, at least for the depth first search. Then another one is the way in which I'm sorting the items, okay. Here I have sorted the items, and this is what I did here. I have sorted the items according to the ratio value over rate, okay, and this will also have an impact on the depth first search, okay. So I'm using here depth first search, okay, and you can see here the objective function that it was able to reach. If I comment here the sorting, okay, I decide not to sort the items. I simply consider them according to the order that I had in the instance file. Okay, so I comment here the sorting of the items. I run this, and you see that it's considering a lot of intermediate solution, but it's not able to find the same quality of solution. So this also is an example of the importance of the heuristic when you implement the branch and bound strategy to solve discrete optimization problem.